Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's Battery Technology Online webinar, 5 Critical Factors to Consider when Potting and Encapsulating Your EV Application, sponsored by Epic Resins and broadcast by Informa. I'm Bob Sperber, and I'll be your moderator today. We have just a few announcements before we begin. This webinar is designed to be interactive. The docker widgets at the bottom of your screen will allow you to learn about today's speakers, download resources, share this webinar via social media outlets, and participate in the Q&A session that takes place at the end of our presentation. The slides will advance automatically throughout the event. You may also download a copy of the slides via the resources widgets. Toward the end of our webinar, we will ask you to complete our survey found on the right-hand side of your screen. Please take a minute to fill this out before leaving us today, as your feedback will provide us with valuable information on how we can improve future events. Lastly, if you're experiencing any technical problems, please click the Help widget found at the bottom of your screen, or type your issue into the Q&A area, and we'll be glad to offer one-on-one assistance. With that, I'm going to hand things over to Matt Venus, Technical Sales, Battery and EV Product Manager. Matt, take it away.
Thanks for joining us. Today, our Senior Development Chemist, Joe Stoller, will discuss the 5 critical factors to consider when potting or encapsulating your EV application. A little bit about Epic Resins. Epic is located in southeast Wisconsin, and we have been a custom formulator and manufacturer of epoxy and polyurethane materials since 1958. In our over 60 years of formulating, we have a profound understanding that not every application is the same, and we are able to formulate or adjust our current products to meet our customers' application requirements. We do this by utilizing our cutting-edge laboratory, which includes FTIR, multi-mass spec, nuclear magnetic resonance, TCI thermal conductivity tester, thermal chamber, DSC, TMA, Instron, HiPot, and other electrical testing equipment. All tests in our laboratory are done in-house on our equipment to an ASTM test standard. Our production and warehouse facility includes approximately 75,000 square feet, which houses over 10 high-speed dispersers, multiple vacuum pumps, and our farm of raw material bulk tanks. Epic's core chemistries are epoxy and polyurethane thermoset materials. We have well over 3,000 epoxy and polyurethane formulas and service over 1,500 customers worldwide, serving 6 continents. Epic Resins is ISO 14000 and 9001 certified. Joe Stoller will now begin discussing the 5 critical factors to consider when potting or encapsulating your EV applications.
Thank you, Matt, and thank you everyone for joining us today. So today we're going to be covering the 5 critical factors for choosing a potting and encapsulating compound for your EV application. Those 5 factors are thermal properties, environmental conditions, material properties, process considerations, and material handling considerations. Before we start with thermal properties, I want to address one of the most important aspects of EV applications, and that is thermal management. The world we live in is dynamic, and one of the most obvious dynamic properties is temperature. All day long, the temperature around us changes, and EV applications magnify this variation. So specifically, what is thermal management? There are 2 main answers to this question. The first is how a material protects a device from environmental variation. For example, a potted ECU will see large temperature variations, which translate into expansion and contraction. Choosing a potting material that protects the ECU during this expansion-contraction manages the stresses caused by temperature variation. So for example, you have different components throughout the board, and this potting material, as it expands and contracts, is a soft, pliable material, so it's going to give to any expansion and contraction, protecting those components. The second is how a material controls the thermal energy produced by a device. For example, motors used in EV applications generate large amounts of heat. Dissipating this heat is critical to improving performance and longevity. Motor encapsulants should have high thermal conductivity for this reason. In this cross-section of an EV motor, these coils generate a lot of heat. This heat needs to be dissipated through the potting material to the outer shell. This potting material needs to have high thermal conductivity in order to accomplish that. Then why is thermal management important? If the appropriate thermal management is provided by the potting compound, it will improve application performance and reliability, which also helps to prevent premature failure. So again, talking about reliability and importance of thermal management, you have this potting material again that is potted underneath these heat sinks. The potting material provides contact with the heat sink to dissipate the heat generated from the ECU. So getting into the critical factors, the first critical factor are thermal properties. So thermal conductivity, the most obvious property, is the material's ability to transfer heat, primarily expressed in watt per meter Kelvin. For example, in this demo that we're showing you here, this shows 3 different materials. The material on the bottom left has low thermal conductivity, the material on the bottom right has medium thermal conductivity, and the material on the top has high thermal conductivity. And you can see this visually. As the material is heated, the material on the top gets hot faster than the other two, obviously showing that it's pulling the heat from the hot plate faster than the other two materials. The second property that we would consider is glass transition temperature, also called TG. This is the temperature when a material changes from a rigid glass type material to a soft pliable material. A third property is coefficient of thermal expansion. Now this is the rate of expansion over a temperature range. We evaluate TG and CTE using a thermomechanical analyzer, also termed a TMA. This measures the height of a sample when ramped through a temperature range. The image we are showing here is the graphic result of a TMA. At the low temperature portion of this graph on the left, you see a slope from -40 to about 0°C. This is the CTE at that temperature range. We call this the pre-TG CTE because it is at a lower temperature than the TG. As the temperature increases to the right, we see an inflection point in the graph at about 60°C. This is the TG. Below this temperature, the polymer is considered a rigid polymer, and above this temperature, the polymer is a soft, pliable polymer. Continuing to move up the temperature to the right of the graph, you see another slope. This is the post-TG CTE, which is higher than the pre-TG CTE. It is important to understand where the TG of the polymer is relative to your operating temperature range to reduce component stresses that occur during this thermal transition. A fourth property is cross-link density and hardness. Cross-link density is a term used to describe the covalent bonds in a thermoset polymer. Higher cross-link density polymers have higher hardness and thus higher TGs than lower cross-link polymers. So this is a very simple graphic that I have up talking about the cross-link density of a polyurethane. So you see polyol molecules that are mixed with isocyanate molecules on the left reacted onto the right portion of that slide where you see cross-linked thermoset polymer. And you can see those cross-linkings give the material or the polymer rigidity. As you have more cross-linking, again, you have higher hardness and greater TGs. The fifth property would be operating temperature. This is a common question that we get. What is the operating temperature of a polymer? The operating temperature of a polymer is prescribed by primarily 2 types of test data: UL/RTI test data and empirical test data. Generally speaking, these tests are not conducted unless specifically requested during the development process. Here is a quick description of each of these tests. UL/RTI testing, RTI stands for Relative Temperature Index, which is tested under ASTM 746B, which is a group of tests that generally measure mechanical, electrical, and or flammability properties of a polymer after aging over a period of time. Empirical testing is testing run specifically for an application. In many applications, it is more practical to evaluate the critical property of a specific application when aged at the specific operating temperature for that specific application. For example, the electrical properties of a polymer may be irrelevant in an adhesive application, or the mechanical properties of a polymer may be irrelevant in a flame retardant application. Thus, a material would only be tested for a specific property at a specific operating temperature for a specific application. So now we're going to compare 3 different chemistries of potting materials for each of these different properties that we just talked about. So when we discuss epoxies, urethanes, and silicone potting chemistries under thermal conductivity, ultimately all of these chemistries can have the same thermal conductivity, because that thermal conductivity primarily comes from the type of raw materials that we use in the potting material. So when we compare epoxies, urethanes, and silicones in glass transition temperature, epoxies have the highest glass transition temperature possible for these three chemistries. And this comes from the cross-link density that polymer has. Urethanes have more versatility. Because of the raw materials that are available to us, we can make urethanes with low glass transition temperatures and high glass transition temperatures. Silicones, on the other hand, generally have lower cross-link density, so they're going to have lower glass transition temperatures. So when we compare these three chemistries for coefficient of thermal expansion, epoxies can have both low and high coefficients of thermal expansion. And this is based on, number one, the types of filler that we use, as well as the cross-link density. Urethanes also have this ability, and that also comes from their variability of cross-link density and their variability of fillers that we can use. Silicones, because they have a low cross-link density, they're generally going to have a high coefficient of thermal expansion. As we look at hardnesses, epoxies are going to have high hardness, again, due to their high cross-link density. Urethanes have some versatility. We can range anywhere from a urethane having a low hardness, gel type of material, anywhere to A to the D hardness. And then as we talk about silicones, generally those are lower gel materials or shore A, again, because of their cross-link density. When we compare these three chemistries in operating temperature, epoxies have the ability to have high operating temperature, again, coming from its ability to have higher cross-link density. Urethanes have a low to a mid-operating temperature range, and again, this comes from its ability to have higher cross-link density, but not quite as high as epoxies. Silicones have a little bit different chemical backbone, so that allows them to have high operating temperatures. Because of the nature of the pricing of silicones, epoxies and urethanes are excellent replacements for silicones in potting applications. The second critical factor to consider are environmental conditions. When designing a polymer for an application, it is very important to know the conditions surrounding the application. This allows the chemist to choose the correct chemistry and tailor the backbone of the polymer for optimum performance in the application's environment. So some critical factors to consider for environmental conditions are elevated temperature, thermal cycling, thermal shock, chemical exposure, and moisture resistance. For example, elevated temperature would include battery, motor, and ECUs. Thermal cycling, you would have some crossover. So you'd have, again, battery, motor application, ECU, heat sensors. Thermal shock could include transmission, door handles, backup sensors, battery, and tire pressure sensors. Chemical exposure, transmission, battery applications, motor, electrical control units, and door handles. Moisture resistance would include headlights, tire pressure sensors, door handles, and backup sensors. So now we're going to compare these three chemistries of epoxy, urethane, and silicone in these different environmental conditions. When we compare epoxies, urethanes, and silicones, for elevated temperature exposure, epoxies really perform the best of these three chemistries. And that's, again, primarily because of the cross-link density. As we have a higher cross-link density, those polymers have better elevated temperature resistance. Urethanes can have good elevated temperature resistance, not quite as good as epoxies, again, because we can't attain as high of a cross-link density as we can with epoxies. Silicones are also in the realm of epoxies in the fact that they have a different chemical backbone, which allows silicones to have good temperature resistance as well. So when we compare epoxies, urethanes, and silicones in thermal cycling, epoxies can have good thermal cycling. It's very important to choose an epoxy that works for your operating temperature range that's outside of the TG of that epoxy. For urethanes, they have really one of the best abilities for thermal cycling because they can have low hardness and low cross-link density as well as high hardness and high cross-link density to tailor for your application. Silicones, because they are softer, have the ability to have good thermal cycling properties as well. When we look at thermal shock, epoxies, again, similar to thermal cycling, have the ability to have good thermal shock resistance. And this comes from prescribing the right epoxy for your application. When we're talking about urethanes, they really have one of the best abilities for thermal shock because when you're using a soft urethane, they have the ability to reduce the amount of stress on your components. Same thing with silicones in that regard. When you're talking about chemical exposure, epoxies would have the best chemical exposure. When you're talking about chemical exposure, it really comes down to cross-link density. Epoxies have the ability to have high cross-link density, which allows them to resist chemical attack. Urethanes, because they can have high cross-link density, have the ability to have good chemical exposure properties. As you have high cross-link density in urethanes, again, that reduces chemical attack. Silicones, on the other hand, are fair. Because they have lower cross-link density, they don't have quite as good chemical exposure properties as epoxies and urethanes. When we're comparing moisture resistance for epoxies, urethanes, and silicones, epoxies really have the best moisture resistance, again, stemming from epoxy's ability to have high cross-link densities. High cross-link density is essentially going to be blocking the moisture from impregnating to the polymer. Urethanes don't have quite as good as epoxies. Again, that's stemming from their little bit lower cross-link density, not quite as high of a TG ability, whereas silicones are fair because they do have a fair amount of ability to be attacked by moisture. When choosing a potting compound, epoxy and polyurethane chemistries have great performance for their cost. The third critical factor would be material properties. We are going to talk about some of the most common material properties that should be considered when choosing a potting compound. Hardness, mechanical properties such as tensile strength, elongation, and modulus, electrical properties, and regulatory compliance chemistry. Now, this is not an exhaustive list, but the most common. When we talk about hardness, there are three main ranges of hardness that epoxies and polyurethanes can fall within. Shore AA, which is a gel type of material. As you get to Shore A, you're talking about the hardness of a pencil eraser or a tire. As you get to Shore D, we're talking about much harder materials, so hard hats or the hardness of a countertop. When we talk about mechanical properties, tensile strength, elongation, and modulus of elasticity, all these properties are evaluated using a universal testing instrument. There are two test methods that are used, ASTM D412 for soft pliable materials and ASTM D638 for higher hardness products. Now, as you can see in this video here, this is our universal testing instrument that's testing tensile strength. And ultimately, we take a sample of a certain dimension based on the ASTM, and we pull it at a certain rate. The results that we get from this give us tensile strength, elongation, and modulus of elasticity. There are many properties that encompass electrical properties. Dielectric constant, dissipation factor, volume resistivity, and dielectric strength. Now, all of these properties have different applications in the electrical field. Dielectric constant and dissipation factor are important properties for RF applications. Volume resistivity is important for power distribution, and dielectric strength would be important for high voltage applications. Now I'll be conducting a dielectric strength test. And then we'll go ahead and trigger the high voltage, and the voltage between those two electrodes is going to ramp up to 50,000 volts until it arcs through the sample, which measures the dielectric strength of the polymer. When talking about regulatory and compliance chemistry, we're talking about RoHS compliance, REACH compliance, Proposition 65 compliance, etc. We have the ability at EPIC to formulate a product to satisfy your regulatory and compliance needs. We'll now compare these properties and these three different chemistries. Epoxies have high hardness, again coming from their high cross-link density. Urethanes have versatility in hardness because we have versatility in cross-link density. Anywhere from a gel material, shore double O, A, and D material. Silicones have a low hardness, anywhere from a gel material to a shore A material. Comparing the tensile strength of these three chemistries, epoxies are going to have the ability to have the highest tensile strength, again, coming from their ability to have the highest cross-link density. Urethanes have a versatility in tensile strength, again, because they have versatility in cross-link density. Silicones are going to have a low tensile strength, and again, that comes from their lower hardness and lower cross-link density. Elongation is going to be opposite of tensile strength. So as you have high tensile strength polymers, you're going to have lower elongation. Epoxies, for example, have low elongation because they're more rigid and have higher cross-link density. Urethanes have versatility because they have versatility in hardness and cross-link density, where we can have both low elongation and high elongation urethane polymers. Silicones are going to have high elongation. They don't have the ability to have low elongation, and that primarily comes from the nature of the backbone of their polymer. The electrical properties of all these chemistries are about the same. There is some differences depending on the specific raw materials that we use to tailor the backbone, but in general they have the ability to have all good electrical properties. So all three of these chemistries have the ability or the potential ability to be compliant, depending on how EPIC can tailor the chemistries for your specific application. Epoxy and polyurethane properties can be tailored to fit the requirements for your EV potting application. Now the fourth factor will be process considerations. Viscosity and process temperature, pot life, gel time, cure time, potting challenges, and dispensing methods. How you will process the material is important to consider. Physical properties are irrelevant if the material cannot be processed or applied in your application. Starting with viscosity and process temperature, this graph is a great example of how temperature affects the viscosity, which helps to improve the flow of a potting compound. In the graph, we show the viscosity of EPIC 0218 at different temperatures. On the left of the graph, at 25C, 0218 is about 80,000 centipoise, thicker than molasses. As we increase the temperature, you can see with the slope of the line that the viscosity drastically drops to 1/10 of the original viscosity at 50C, obviously showing that it flows much better at a higher temperature.
We'll be demonstrating how temperature can affect viscosity and which can help your process when you're potting and encapsulating EV applications. We have the same material here at two different temperatures. Now this is a single component heat-cured epoxy. This material is at room temperature. This material is at 50C. As I pour them, you'll see that one pours much easier than the other. And that shows how temperature, like we showed in the graph a moment ago, can significantly impact the flow and the viscosity of the material. Viscosity and temperature are very important factors to consider when developing your potting process.
So discussing pot life and gel time. Pot life and gel time both describe how a material's viscosity increases. The difference is, pot life is the time that a material is usable or pourable in an application, different from gel time, which is a specific ASTM test that measures the viscosity over a period of time. For example, in this slide, you show two lines on this graph, viscosity versus time. In the first line, you see a very slow increase in viscosity until approximately 10 minutes, at which point the viscosity increases very, very quickly. This is a material that would have a very distinct gel time. Looking at the second line, you see a much slower increase in viscosity. This is a material that would have a specific pot life, or a time at which the material is no longer pourable or flowable in an application.
So we're demoing gel time versus pot life. And in this example, we're going to show you how gel time is a very specific test where we actually measure the viscosity of the material over time as the material begins to react. And this would be what we would call our gel time apparatus, where we have a glass rod that's measuring that gel time. We're also going to be comparing that to the same chemistry of product, but something that has more of a pot life. So as this goes along, we're going to kind of look at the difference in the viscosity between the two and how that material kind of runs off of this tongue depressor. Now, in your application, obviously, it would be flowing in that particular ECU or motor or whatever you'd be potting. But this gives you a good idea of how much flow you have as the material begins to react. All right? Now, these two products over here on this side are much faster reacting, so these have more of a specifically designed gel time that we would run this test with, versus a pot life, again, would be more flow of the material, application specific for your particular application. All right, in a moment you're going to see this one over here. It's going to get to a point where it's gelled, it's not flowing anymore, whereas this one where it has more of a defined pot life will just be building viscosity slowly and slowly. So you can see that viscosity is really building on this one on the right. It's just about to gel, whereas this one on the left still has a nice low enough viscosity to flow, obviously depending on the application, it's pot life. So as you can see, the viscosity is really building past the point of flow, and it's just about to gel. And typically, urethanes will gel in the center, so it's that center that will produce a little bit of a ball in there. You can see that much lower viscosity on this one over here. And this one's just about there. I can almost not pull the stick out without lifting the whole thing. So as you can see here, a very distinct gel of the material. How it is distinct gelled. Very distinctly solid in that center of that material, not flowing at all. So whereas this material would have more of a pot life. So this would have a much slower increase in viscosity. Obviously, this is a specific gel. This demonstrates the distinct difference between pot life and gel time of a thermoset polymer. Cure time is the amount of time it takes for a material to reach greater than 95% cured. Many people will confuse this with handleable time. In many cases, a material can be handled and moved on to its next portion of the manufacturing process before the cure time is complete. Another process consideration is potting challenges. For example, part geometry, component configuration, mass of the application, vacuum impregnation versus non-vacuum potting, and other considerations. Potting geometry is important to consider because you have to consider where the material is going to flow and or where the difficult portions of the material are going to flow. Component configuration is an area where you need to consider that flow, along with the mass of the application, or how much material you need to pump into it and where it needs to go. When you talk about component level damming is areas like this, where you have a narrow area where the material needs to flow. So those things need to be considered. In some applications, there are areas under a board or coils that need to get vacuum impregnation. That should also be considered. Other considerations to mention would be environmental or substrates. You might need to adhere to a certain substrate, or you might need to get good flow around certain substrates that have different surface tension. All those are important considerations when choosing a potting compound. Process considerations of dispensing methods are also important to consider. Are you dispensing a one-component or a two-component material? Is the material have special requirements for processing and dispensing? Single component materials might need heat. Equipment selection is very important, and choosing the right meter mix and dispense company to work with you in that process is also very important. Epic also has in-house dispensing equipment to help you prototype your potting process. The fifth factor is material handling. Understanding how to handle a material starts with understanding the safety considerations surrounding that material, such as proper PPE. In most instances, safety glasses, smocks, and a vapor respirator are primary requirements for PPE. Ventilation is also important to consider. Understanding chemicals. All chemicals have hazards. Even sawdust has a Proposition 65 warning. Thus, proper precautions should be followed. Employee training and SDS. Employees should understand what PPE is necessary for a specific chemistry and how to read and understand an SDS. Material disposal. Because all chemicals have hazards and thus will have disposal regulations. Proper disposal should be considered by your compliance officer. Once you are prepared for the safety considerations for material handling, you also need to understand other material handling requirements. Moisture sensitivity, homogenized material, material prep before use, proper container sealing. In this slide, we're going to talk about moisture sensitivity of urethanes. Urethane components are moisture sensitive and will react with atmospheric moisture. Protecting the urethane component is simple and only requires an inert gas blanket on the A and B components. This graphic shows how increasing levels of water can cause foaming. Urethane potting compounds are elastomers, not foams. When a urethane is contaminated with moisture, it becomes a foam, and we want to protect it so that it doesn't become a foam in your potting application. Homogeneous material are important. All materials that contain functional fillers will tend to settle to the bottom of the container. This is the same reason why it is recommended that paint be stirred before use. In this slide, we talk about a homogeneous material versus a settled material. On the far left, you see the filler evenly dispersed throughout the polymer. The center slide shows partial settling of those solid particles that will slowly fall to the bottom of the container. And on the far right, you have an extreme example of settling where the filler is completely settled to the bottom and the resin is above that. This is an extreme example of filler settling and not typical for most products, but is an important property to understand when using a filled material. In instances where homogenization is required, material prep before use is essential to make sure that the filler is properly dispersed in the resin. Material prep also includes degassing material as needed after rehomogenation. Proper container sealing is purging the headspace of partially filled containers with argon or dry nitrogen to protect them from moisture contamination. So that concludes the technical portion of this presentation. We'll hand this back to Matt for some more information on Epic resins.
Thanks, Joe, for giving us an overview of the 5 critical factors to consider when selecting the right epoxy or polyurethane. Epic Resins is able and ready to be an extension of your engineering team. We will formulate or provide a material to fit your specific and unique product. Our team is ready to utilize the physical testing equipment in our lab as well as our meter mix dispense equipment to help meet engineering timelines. Our qualified technical sales team and the chemists will work with you on providing the right material. Thanks for attending this webinar, and please contact us with any questions.
Thank you. Now, before we begin with today's Q&A, please direct your attention to our webinar survey available on the right of the presentation window. If you close the survey on your screen, you can reopen the widget by clicking the icon along the bottom of your screen. Thanks in advance for filling out the feedback form, by the way. Your participation in the survey allows us to better serve you. And now on to the Q&A portion of our event. As a reminder, to participate in Q&A and questions and answers, just type your question into the text box located to the right of your presentation window, or click the Q&A icon at the bottom of your screen. If we're not able to answer all submitted questions during today's webinar, we'll be sure to share them with our speakers who can reply to you offline. Thanks very much. Let's get right to it. Question, is that TG and operating temperature the same thing?
So Joe Stoller here. Thank you everyone for joining us today. So the TG is not the same as an operating temperature. So the TG is the temperature at which a material goes from a rigid glass material to a soft, pliable material. Whereas an operating temperature, like we talked about in the presentation, is a group of tests, either UL, RTI testing, or empirical tests, that give you an idea of how a material responds to temperature over time and how the polymer or the properties of the polymer will change over that time period.
Mm-hmm. Okay. What is your definition of high thermal conductivity?
So that's going to depend a little bit on an application. So what might be a high thermal conductivity in one application might not be high enough for another. To give you a few examples, unfilled materials are generally going to be around 0.2 to 0.3 watt per meter Kelvin. As you have different types of fillers that are in a potting material, that's when you're going to start to have some thermal conductivity. Typically, that's below 1 watt per meter Kelvin. As you get into materials that are specifically designed to be better at thermal management, that are going to have what we would essentially call thermally filled, then you're going to be looking at greater than 1 watt per meter Kelvin.
Very good. What's the range of thermal conductivity that your products have?
Matt Venus here. Our products will carry anything from the unfilled systems at around a 0.1 watt per meter Kelvin, all the way up to over 3 watt per meter Kelvin. Most of the time we're looking at finding the right product that meets the application. Obviously, when you look at going up higher in thermal conductivity, there are other things that happen, such as an increase in viscosity, but the range is anywhere from 0.1 up to greater than 3 watt per meter Kelvin.
Very good. Do you have a clear or unfilled? Excuse me. Do you have a clear or an unfilled thermally conductive material?
Yeah, there is going to be some thermal conductivity to a clear system. It's going to be relatively low, though. At this point in time, the lab does not have we have not formulated a thermally conductive clear system, but it is something. There's always projects that the lab is working on, and they seem to pull surprises out.
Mm-hmm. Mm-hmm. Next question we have is it possible to formulate a high TG material that doesn't require a high temperature curing?
No. TG is going to be dictated by the temperature that the material is cured at. In order to attain that high TG, you need to have the curing temperature to attain that TG temperature. Without that, during the curing process, you don't get enough molecular motion in order to provide enough cross-link density. So you do need to cure to the TG that the material is prescribed to have.
No, I guess some of that would depend on what is considered a high TG, and I do know mass dependent, and where your peak exotherm is going to be.
Absolutely.
Because peak exotherm will help drive a cured TG. So if you're in a larger mass and you're going to see a relatively decent amount of exotherm, that's going to obviously drive that TG up. And I think it's important to note what is considered, what you're looking for is considered high TG as well.
Very good, very good. Next question. What is recommended for use in LED lighting applications where an optically clear solution is needed, epoxy or urethane?
I would tend to lean towards aliphatic urethane material for an optically clear LED solution, mainly because of the UV stabilities.
We've seen it in a lot of customers that have come to us that they've been offered epoxy systems which are not aliphatic, which can yellow, they degrade under UV light quite rapidly. So we, like Matt was just saying, recommend aliphatic urethanes for those applications. They have a lot better longevity over time.
Very good. Next question. Should I use pot life or gel time to spec in my process?
Sure. So really, gel time is the best way when you're looking at a specification, because remember from the presentation, pot life is more application specific. So for one application might have a pot life that's completely different from another. A good way to talk about this is ultimately think about you're pouring this material, and the larger area you have to pour in, the smaller intricate areas it's going to be more difficult. So that's going to have a different pot life from those larger areas. So really, you want to use a gel time, because that's a specific ASTM test that again, with the right equipment, you can have that as an incoming QC test to verify that in your end, along with what we test when we're manufacturing the product.
Mm-hmm. Thanks. What's the normal shelf life of the materials?
Sure. So that's going to vary depending on the chemistry. So for unopened materials, start at 25C. Generally speaking, we give two-component epoxies a 12-month shelf life. For urethanes, under those same conditions, you're looking at a 6-month shelf life. Single-component epoxy systems, now those vary. Generally, those are formulas that are the chemistry requires refrigeration. And those range anywhere from 1 to 2 months to 3 months in refrigerated storage. However, Epic Resins also has single-component chemistry that can be room temperature stored, and we have 10-month shelf lives at room temperature on some of our single-component chemistries that have excellent adhesion and really great high TGs as well. So we have quite a variation of shelf lives depending on your needs.
Very good. During operation, are you above the TG? Does that reduce the lifetime of the product?
Not necessarily. It depends on if those are excursions or if those are if it's operating above its TG. And that answer is also dependent on the sensitivity of your components in your application. So remember looking at that graph when we transition through the TG, there's a lot of stresses that occur during that temperature range. So if you're constantly going through that temperature range, think of it kind of like taking a paper clip, the wire of a paper clip, and bending it back and forth. Going through the TG kind of does that to all your components. So that's why we recommend being either below or above the TG, because again, as you transition through there, you're constantly bending that paper clip back and forth, and after so many bends back and forth, it's going to break.
Very good. How do the mechanical properties correlate with the thermal properties? For instance, elongation to CTE.
I'm not sure I understand the question completely, but let me try to answer. So, when you have a high TG, you're generally going to have high tensile strength. Okay, so there's a correlation between those properties. However, that doesn't necessarily mean that you're always going to have a high tensile strength with a high TG. If you were to compare two TG materials that have the exact same TG, you could have one that has a higher tensile strength than another. And that's going to be dictated, again, by the raw materials we use on the polymer side, but there's also functional fillers that we can add in that can kind of adjust some of those properties as well. I hope that answers your question.
Okay. Me too. Thanks. Do you already have epoxies on market for EV motors?
Absolutely. Absolutely. We have both two-component materials, single-component materials on the epoxy chemistry, and two-component urethane systems as well.
Mm-hmm. Can you tell me just to clarify, like, for which applications? Once again.
Well, for EV motors, absolutely. So we have complete potting and encapsulation of the stators. We also have varnish materials, both as single-component as two-component materials as well. So we formulate, just so that everyone's aware, being a custom formulator, we're a problem solver for our customers. So the idea is that when a customer has a specific process they want to meet, certain properties they want to accomplish with the material, that's what we're formulating. So we have a lot of different areas that we currently serve because of that.
Very good. And do you have a low temp, approximately like 60 to 80 C thermal cure epoxy or epoxies, and how long is cure time?
Sure. So that's going to depend on the chemistry that we use. So when we're talking about epoxy cure time, that's dictated primarily by the curing agent that we're using. So the short answer is yes, and we can formulate to accomplish the cure time you want at the cure temperature that you want as well.
Is urethane susceptible to moisture after it's fully cured?
Absolutely, yes. So it can be, that's we talking a little bit in that slide that, so the backbone of the polyurethane does have some portions that can be attacked more by water than epoxy systems. However, depending on how we formulate the cross-link density of the urethane, we can adjust that along with the type of raw materials. There are certain types of raw materials that have more or less, they're more or less hydroscopic when cured. So again, tailoring the backbone of that final thermoset polymer to accomplish the properties that you want to in your final application.
And the urethanes are still formulated in order to protect the parts of the circuitry or whatever the application is against moisture getting to the main level or to where you don't want it to go.
Mm-hmm. Is it possible to have longer pod life in the polyurethane system?
Yes. So urethanes have a unique property in that we have a more latitude in adjusting reactivity with urethanes. And not to say that we can't do it with epoxies, but epoxies are, again, like I was saying before, are kind of dictated by the reactivity of the amine group, which dictates the cross-link density and obviously how it reacts. Whereas with urethanes, we can catalyze those systems to have essentially the same polymer that could have anywhere from a 2 to 5 minute gel time at room temperature and 100-gram mass to 50 to 60 minutes or longer.
Mm-hmm. What mechanical properties best correlate to passing thermal shock requirements?
I wouldn't say that those necessarily correlate at all. It's application specific, and normally you're talking thermal shock. In our experience, a softer polymer, so lower tensile strength, is generally better suited to pass those types of tests.
Yeah, we're looking when we look at the thermal shock on a material or selected material for that. There's a lot of different considerations in there. Application is obviously the number one, and what the material demand or the part demands might be. In some cases, we're looking for a very low glass transition coupled with a low hardness, and understanding the CT is going to be high. In other applications, we're looking for very, very low CTE, maybe an elevated TG, and understanding that the hardness might be higher. So it is application specific, but those are things that we are taking into consideration when selecting a material.
Mm-hmm. Is it possible to specify a potting material that will have minimal effect on the tuning of a board-mounted chip antenna? Excuse me, Matt. Such as what would be on an integrated Bluetooth module?
Sure. So RF applications, absolutely, yes. We do a number of those, and that comes down to the type of raw materials that we formulate into the system, and we're very well versed in providing the polymer backbone for you to tune your RF application.
And we've also seen really good success when the chip or the antenna is able to get tuned as well, and kind of work on adjusting that to match a material. That really has
very good. Mm-hmm. Sorry. Let's see. We have so many actually. Here we go. Do you find it necessary to vacuum pot for motor applications?
Every application is a little bit different. Vacuum potting is going to get the best impregnation, especially if you're dealing with filled materials and higher thermal conductivity. You're going to want to utilize heat and some vacuum to get the absolute best impregnation.
One thing that is really great about my job is that we'll have customers that will ask that question that will come in and it could be vacuum potting or whatever else. But we have the ability here to do some prototyping. So if a customer says, hey, I'm not sure which is the best process to use, we can certainly do some in our facility here, vacuum potted, unvacuum potted, or vacuum potted at different pressures. So we have those abilities.
Thanks, Joe and Matt. Re-asking my previous question we had to clarify, someone wants to know, using different words, when investigating component failures, how does one rule out potting failure?
So a couple ways we can do it here is, so we have an FTIR microscope. So we can actually do sectioning of a customer's component and do an FTIR analysis of different cross sections to determine whether the polymer itself had any failures either from a thermal standpoint, from a processing standpoint, and we can determine that with FTIR and comparing unthermocycled polymer to thermocycle or thermoshock or whatever environment that polymer was in using that FTIR technology.
I hope that does it. Do you have e-motor potting prototype capabilities in the U.S.?
I'm sorry, could you say that again? I missed that.
Yeah, do you have e-motor, potting prototype capabilities in the U.S.?
Absolutely.
Yes. At our facility in Wisconsin, we have vacuum chamber capabilities as well as the capability of dispensing material under vacuum in order to run demo units and prove out materials.
All right. Well, Joe and Matt and everyone who attended, we have a large group here today. Thank you. That's all the time we have for questions today. But we appreciate your time and expertise to the presenters, and thanks to Epic Resins. And thank you, everyone in the audience. We appreciate your attention and participation. And within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. And please feel free to invite your colleagues and peers who may not have been able to listen to the event. This webinar is copyright 2021 by Informa. The presentation materials are owned or copyrighted by Informa Markets. And the individual speakers are solely responsible for the content and opinions. And I'm Bob Sperber, and I thank you so much for your time, and have a great day.